So before starting the study of extension fields, I want to go to this thing called the quotient field construction. This is a construction that starts with a domain S, so S, an integral domain, and produces a field called the fraction field of S. A field that contains S and is sort of the smallest field that contains S in some sense. I mean, really, this construction is nothing more than abstracting the construction of rational numbers out of integers. You know, you can think of a rational number 3 over 5 as the ordered pair of integers 3, 5. Except you need to have a way to identify the pair 3, 5 and the pair 6, 10, because the number 3 over 5 and the number 6 over 10 are the same number, right? So you need to have a way to identify these. And the tool that mathematicians use to make this sort of identification is an equivalence relation. We have seen this before. So I have a reminder of equivalence relations. Here, let's go through that quickly. If A is a set, a relation R on A means a subset of A cross A. So if A comma B is in R, we will write A R B, and we read this as saying that A is related to B via this relation R. So two examples, maybe this is a relation on real numbers, right? Less than or equal to is a relation of real numbers. One way to describe this relation is to prescribe you this set, the shaded part of the plane. This set R is a subset of R reals cross reals. And I claim that describing this set is same as describing the less than or equal to relation. In what sense? In the sense that a point is in the shaded part if and only if the first coordinate is less than or equal to the second coordinate. X comma y is in R if and only if x is less than or equal to y. Let's say x is related to y. Now let's say x and y are integers. Let me define a relation on Z. If x my congruent to y mod 5. So this is a relation on Z. That would be a relation of the kind that we want to study actually. So for example, via this relation 7 and 12 are related. Two things are related via this relation if their difference is divisible by 5. So is 17. But 7 and 11 are not related. This is an example of an equivalence relation. A relation R on a set A is called equivalence relation if the following three properties hold. The relation is reflexive, which means that every element is related to itself. The relation is symmetric, which means that if A is related to B, then B is related to A. And the relation is transitive, which means that if A is related to B and B is related to C, then A is related to C. When you have an equivalence relation, what you get out of it is a partition of the original set A. This is how you take an element and look at all the other elements in A that are related to it. This subset is called the equivalence class of A here. It's all the B's in the set that are related to A. And because of transitivity, this property, these guys are also, and symmetry, these guys are also going to be related among each other. And then if you take something that is outside this collection, here are all the things that are related to C. And these guys are also going to be related to each other. But none of these guys, none of the friends of 3C are going to be related to any friend of A. So nothing in one chunk is related to anything in the other chunk, but everything in the single chunk are related to each other. And the whole set sort of splits into these chunks, these subsets. And this gives us a convenient way to identify all the elements in one chunk. That's why this is useful, this construction. So I'm gonna write A mod R to be the set of these chunks, the set of equivalence classes. So this is all these sets. So an element of A mod R is one of these subsets. This is one element, this is another element, and so on. So for example, we used this construction before already. Z mod 5, for example, is the set of equivalence classes for this equivalence relation. The equivalence relation where two numbers are related if and only if the difference is divisible by 5. And we'll use the same tool to make the quotient field. We make some space here. So I want to take pairs of elements of S. So I want to take A to be pairs like this, where A and B are from S. So it's a subset of, so this would be really S cross S, but I don't want B to be 0 because I want to think of, out of this pair, I want to sort of make this this element A over B, whatever that means. So secretly I'm thinking of A comma B as A over B. So I don't want B to be 0. So this is some subset. This is some subset of S cross S. And define a relation V. I'm going to denote the relation like this wiggly sign. On A by one pair is related to another pair if, let's see, you want to say that 3 comma 5 is related to the pair 6 comma 10. Really the ratios are the same. How do I say that the ratios are the same? Only using the operations in Z. The way you say it is that this times that should be same as that times this, right? 3 over 5 equals 6 over 10 is same as saying 3 times 10 is 5 times 6. And that's purely a statement in terms of integers. So we define a relation wiggle 1A by saying one pair A comma B is related to another pair C comma D if and only if AD is BC. And here I'm using the multiplication of the ring S. And then the exercise is to verify that this is an equivalence relation. That's rather straightforward. Verify that this is an equivalence relation. On A. And we let frac of S be the set of equivalence classes. A mod the relation, set of equivalence classes for this equivalence relation. And I'm going to write the equivalence class of a pair A comma B as A over B. Okay. And then you have to do various things. You have to define an addition on this, a multiplication on this, and then you have to identify S inside it and show that this frac S is actually a field. Instead of writing square bracket, and then parenthesis, we'll just abbreviate this as AB. Okay. Let's not write A over B yet, just yet. Let's just write AB. But now secretly you're thinking of this as A over B. First thing I'll do is identify S inside frac S. You need to identify a number, an element A with the number A over 1. So A comma 1 square bracket. Show that this is a injection. Show this is an injective map. So there are lots of little exercises to be done, but they're all straightforward. And now you define plus and dot on this frac S. Let's give this frac S a name, T maybe. K maybe. K is a good name for a field. The addition is going to be looking a little funny. But you know what it has to be. This is really doing A over B plus C over D. So this should be AD plus BC over BD. So that's what I'm going to let it to be. And the multiplication will look simpler. It's going to be just ACBD. You notice, so now you verify next exercise that plus dot make K into a field. I already have a 0 and a 1. Once I have identified S inside there, where 0 means this and 1 means that. So 0 over 1 and 1 over 1. Okay. And the inverse of AB is BA. K over B inverse is B over A. If A is non-zero. Okay. If A is 0, then you can check that 0B is same as 0,1. So the non-zero entries are all of the form AB where A is not 0. And so this is a field now, and then S is sitting in. Finally verify that S is a subring. This map, really, more precisely, this map I identifies S as a subring of the field frac S. And actually you can prove that this inclusion has the following universal property, whatever that means. The following property, that whenever you have a injection from S to a field M, that map actually extends to a map to the fraction field in a unique way. So given any alpha, I have this I anyway, you can find alpha twiddle from the fraction field, so that applying I and then applying alpha twiddle is same as applying alpha. So in that sense, this construction is canonical. And if you apply this construction to the ring of integers, you get rational numbers.